Very well. Let's move on to a next topic. The next topic is related to generating sigma-algebras. So when we work with sigma-algebras, we want to kind of have a convenient sigma-algebra at hand where we can compute things on the object that we want to compute. Remember, sigma-algebra is the collection of measurable sets. A sigma-algebra is the collection of sets that we will be able to assign a probability. So the sigma-algebra will be our fundamental collection of events where we can give probabilities and define them. For example, think about the open sets on the real line. So it's quite natural that we would like to have a probability, a random variable or probabilities on the real line, and we would like to assign a probability for every open set. But now we learned that the open sets, they don't constitute a sigma-algebra by themselves. So what to do? We would still want to calculate probabilities for this. The problem was that, okay, the open sets are quite nice structure, but we ran out of the open sets when we were doing these intersections and unions. So we kind of got out of the nice collection, the open sets. So what to do is that we need to increase the collection and to something bigger that contains the open sets. But kind of let's extend the framework to something bigger that contains the open sets, but something bigger that is big enough so that it's stable under the intersections and unions as we want. Okay, so we need to extend the collection of sets, the collection of open sets, to some bigger framework which is stable enough. That's the idea of generating sigma-algebras. And how to do it. Here is how to do it. Here is the definition. And the definition is like this. We take any collection, C, so take any collection of sets. Maybe it's the collection of open sets. Maybe it's the collection of some very nice, your favorite sets in your favorite space with maybe nothing, no structure at all. So whatever is C. And then we define sigma of C as the smallest sigma-algebra, which contains all of these members of C. So we say that the sigma of C is the smallest sigma-algebra, which contains the collection C. And this is very, very abstract way of doing things, but then we say that, okay, let's call this the sigma-algebra generated by the collection of C. That's it. So in a way, this is your kind of blunt way of doing that. Okay, we extend as much as we need, but not more. To make something which is not sigma, we make it sigma-algebra by extension. Does it really work? Does this definition make any sense? Is it doable? Let's look at this and let me try to convince you that it is doable. This makes sense. It looks very abstract, but let me try to convince you that it's not nonsense. So to do this, let's open some notes where we can write a bit. Let's see if I have here a notepad. Here, yes. Here is a notepad. I'm using Microsoft OneNote to write something. Can you see a notepad? Give me yes if you can see it. Thanks. On the notepad, there's the definition. There's a definition of sigma algebra, and that's just taken from the lecture notes. And then in the notepad, okay, let's see. The generated sigma algebras is here. So this was the definition that we just looked. To understand that this makes sense, we need a lemma first, and the lemma is here. What does the lemma say? It says that take any collection of sigma algebras, F alpha, and let's define F as the collection. So we define F as the intersection of these sigma algebras, and we claim that this is a sigma algebra by itself. That's our claim. How to prove it? Let's see if I can fit the proof here. Let's prove this lemma. So we claim that F here is a sigma algebra. How to do it? Well, we need to check the three axioms. So first, does omega belong to F? Is the full set a member of F? Well, we know that the full set belongs to F alpha for all alpha, because F alpha is a sigma algebra. So then, because this is a sigma algebra, it contains the full set. But if this is in every F alpha, so then it follows that omega is also a member of the intersection of F alpha. And that means that omega is a member of F, because this intersection is F. That means that the first property is okay. What about the second property that we require? Does F is F closed? Is F stable with complements? So imagine we take set from F. Then what does it mean? It means that E belongs to F alpha for all alpha. Yeah, and every F alpha is a sigma algebra. So every F alpha is closed under complement. So that means that the complement of E is also in F alpha. And that's true for every alpha. So that means that the complement of E is also a member of the intersection of F alpha when we take all F alphas. And that means that the complement of E is actually in F, because that intersection was F. The second property is okay as well. Then we have third property. Let's see. Let's put it down for a while. The third property, we assume that we take E1, E2, we take an countably infinite list of elements in F, and we ask, is the union of these also in F? So let's see what happens. Now, this condition implies that each of these, En is in F alpha for all alpha and for all n. And so that means that because F alpha is a sigma algebra, it follows that the union of En belongs to F alpha as well. And that's true for all alpha. Because it's true for all alpha, it's also true that the union En is a member, because that's true for every alpha, so then it's true for the intersection of these collections alpha in I. And that is F, so that means that the union is in F as well. So the third property is okay as well. And now what we did in this proof is that we checked, okay, omega belongs to F. We checked that F is complements. and we found that the F is closed under countable in unions. Yeah. Okay. And there's a question by Elias that yes, can the index set, when we look at alpha in I, the index set, can I be uncountable? Yes or no? Well, look at the proof. What if I is uncountably infinite here? Does something change in the logic of part one? Think about now. Omega is in F alpha for all alpha. Okay. Each of these is a sigma algebra, so it becomes means that yeah, omega is in F alpha for all alpha. So omega is in this intersection, even though I is uncountably infinite. And if you look at this carefully, it doesn't matter if that I would be uncountable. And it actually doesn't matter in each of these parts of the proof. So yes, indeed, we can conclude that let's make a note. I can be uncountable. And that's actually really crucial here. So the boundary between countable and uncountable, sometimes we can cross it. Here we can cross it. So we can do some lemmas for uncountably infinite index collection for this. Now let's be careful. We are looking at the intersection of the sigma-algebras. So we are looking at the intersection of the collections of sets. This is how the lemma works. Why is this lemma so important? It is because that helps to prove the corollary. The corollary is that this definition does make sense, this sigma-algebra generated by the collection. We are getting short on time, but actually what we will do, I think I have 2 minutes left of the lecture. So what we will do now is that I will do this remaining proof for the corollary. I will do it during the next 15 minutes. And you are free to go because you probably have something else to do at 12. But I will continue for 15 minutes, and this 15 minutes will be delivered on video. Or if you can stay now, you are free to stay. And I will go 15 minutes overtime. That means that 15 minutes will become online in the videos this evening. Okay. So let's now prove that this definition of the sigma algebra does make sense using the lemma. And what we need to do, we need to check that the sigma of C is a sigma algebra, that such thing exists. And let's do it here. So that's what's called the corollary 1.9 in the lecture notes. What does it say? It says that if we take any collection of subsets of omega, the claim is that then there exists a small sigma algebra containing C, and it is unique. Let's look at the proof of this. Let's first think about uniqueness as part one. Uniqueness. So could it be that assume that this smallest sigma algebra that we used to denote by sigma of C, assuming it exists. So assume that there are two kind of this type of things. So assume that we have F1 and F2 are both smallest in the aforementioned sense. Then what happens? Then we know that F2 is sigma algebra containing C. And we know that F1 is because F1 is smallest, so then F1 is smallest such thing. So because F1 is smallest thing with the property of being a sigma algebra and containing C, we conclude that F1 must be contained in F2. That's what we mean by smallest. But then symmetrically, then also F1 is sigma algebra containing C, and F2 is smallest. So we reverse this F1 and F2. We conclude with the same logic that F2 is contained in F1. And if we combine these two observations, we conclude that F1 is actually equal to F2. So that means uniqueness. There can be at most one smallest collection of sets being smallest and containing C. Okay. That sort of trivial thing, it's kind of just an exercise in abstract notation. The more interesting or less trivial thing is related to, let's see, I have a little problem with my OneNote software. Let's see. It seems to be more visible there than should be. Let's change screen a bit and see if the problem goes away. Okay, I see one box that shouldn't be there, but let's not worry about that. And let's look at the part 2, existence. So how do we prove that there exists a smallest sigma algebra containing a collection C? Sometimes we do it by proving, oh no, this is now failing me, this Microsoft software. What should I do? Because it fails. Let me close it and open it once. So it will disappear. I close it and open it. Let's see if there's a bug in the software. We open it again. We'll do a screen share again. Now, I think we can see it. Yes, and the bug seems to have gone away, hopefully. I'm clicking draw. Yes, I can draw. Okay, yes, I think. Can you see the OneNote now? Show me green light if you can. Thanks. So let's do the existence part. How do we do it? Let's say we define, let's define sigma of C as, how do we define it? We define it as the intersection of all F. We take the intersection of all F with in a certain collection where S is the collection of all sigma algebras on omega containing this collection C. And now we take the all sigma algebras here. This sounds quite, taking the all sigma algebra sounds quite ambitious because we know that there are uncountably many collections here, essentially, whenever this omega is not finite. So, but anyway, now by lemma, 1.8 that we just proved, we know that the sigma of C is a sigma algebra. It makes sense, right? So this type of very abstract collection does produce as sigma algebra. Is this collection non-empty? Okay, it is because the power set is here. So let's note that this collection is non-empty. We are indexing, we are intersection by non-empty because the power set on omega is one of the members of S. Yeah. This is a sigma algebra, and because it's the power set, it contains C trivially. So that's why this strange intersection makes sense, and it even is a sigma algebra, as we noted here. And then we claim, okay, we ask, does sigma C contain C? Well, let's check. Assume that we take one member of C. So let's pick some set in the collection C. Then E, this set belongs to F for all F in S by the definition of S. And that's why E belongs also to the intersection of F in S. And that means that E belongs to the sigma of C. So the answer here is yes. We are looking at the collection where every member of this collection contains, or every member of this collection is also contained in this collection. Okay. And then we still ask, is this the smallest? So we are actually asking, finally, is sigma of C or let's say a smallest element of S? And let's study this. So if we pick some member of S, so assume that we take some member of this collection S, so we take some sigma algebra containing C, then what happens? Then the sigma, C belongs to G because for any set in the sigma C, well, if E is in sigma C, so it means that E is actually, by definition, it's in the intersection of F, where F goes through S, and that means that, of course, that G is one of these, so E belongs to G. That's why this is true. And hence, think about for any G, this sigma C is contained in G, so that means that sigma of C is the smallest. Okay, is it a or the? We already proved that this is unique, so it is the smallest member of S. And this is, of course, this ordering with respect to the subset order. So what we have proved. Let's see. We looked at this kind of abstract collection S, all sigma-algebras containing C. And we noted that this sigma of C defined this way is a sigma-algebra. It is a member of S, and it is the smallest member of S. So actually, this concludes the proof of what we wanted to do. We prove that for any collection, there does exist the smallest sigma-algebra with the property that it contains C.